Hello everyone. First of all, I would like to thank Hongbin and Lang for their organization and invitation. My talk title is Joint Likelihood Inference for Semi-Parametric Nonlinear Mixed Effect Models with Covariate Measurement Errors and Change Points. This is the joint work with my former PhD student, Dong Wei. This is the outline, the introduction, and then I talk about the research motivation. After that, I gave some notation and framework. In this research, we proposed two likelihood estimation methods. One is called MCEM, implemented by the Monte Carlo EM algorithm. Another one is called the APPR method, where I apply approximate log likelihood functions by using a first-order Laplace approximation. We illustrate our methods in a real data example in 8 studies. We also have conducted the simulation studies. Here I would like to share some results. The last part is conclusions. Semi-parametric nonlinear mixed effect models have been widely used in longitudinal studies. These parametric nonlinear mixed effect models, however, may not be flexible enough in modeling complex longitudinal data. So semi-parametric nonlinear mixed effect models have been proposed. In many longitudinal studies, the inter-individual variation usually receives greater attention, and this variation may be partially explained by time-varying covariates. But some covariates may be measured with substantial errors and may contain missing values as well. Ignoring the measurement errors and missing data in covariate may lead to biased results. Moreover, there may exist change points on some responsible longitudinal trajectories for various regions, such as drug intolerance. In this research, our objective is to simultaneously address measurement errors and missing data in time-varying covariates and change points on response trajectories for semi-parametric nonlinear mixed effect models. Our research is motivated by HIV viral dynamic studies, which have been popular in AIDS research in recent years. Semi-parametric nonlinear mixed effect models are shown to be powerful for modeling complex long-term HIV viral dynamics. In these models, the inter-patient variation may be partially explained by covariates, such as the CD4 cell count, but some covariates may be measured with substantial errors and may be measured at time points different from the response measurement schedule, which leads to missing data in covariates. In addition, some of viral loads may rebound at the later stage of the treatment due to the drug intolerance or other problems. There may exist rebound points on viral load trajectories. Such rebound points may be an important indicator to help quantify the treatment effects and improve management of patient care. Therefore, it's important to address rebound points as well as CD4 count measurement errors and missing data in modeling viral load trajectories in order to obtain reliable results. Figure A shows the viral load trajectories during an anti-HIV treatment for 4 randomly selected patients. We can see that viral loads decay rapidly in the initial period, called the first phase viral decay, and then decrease gently, called the second phase viral decay. That exhibits a clear pattern and may be modeled parametrically. However, some of viral loads may rebound at a late stage of treatment due to drug intolerance or other problems. Note that viral load trajectories after the rebound points can be quite complicated, so non-parametric modeling may be appropriate. We also observe that there is a large interpatient variation, which may be partially explained by time-variant covariates, such as CD4 cell count. Figure 4b shows the CD4 cell count trajectories for 4 randomly selected patients. Mixed effect models may be helpful for describing CD4 count precise. Now I talk about the notation and the framework. Suppose that we have n individuals in a study. For individual I, the YIG is the response value at time TIG, G from 1 to Ni, and the YI is the response vector collecting all observed response values for individual I. Tau I is the time to the change point on the I's response trajectory, subject to right censoring. The observed time is change point to change point Ti is the minimum Tau I and Ti Ni. Ci is the censoring indicator, which is Ci equal to 1 if we observed the time to change point, otherwise 0. ZIKL and ZIKL star is observed value possibly measured with error and unobserved true value of covariate K as time UIL. Here K from 1 to nu, as that means we have new time varying covariates with measurement error. L from 1 to MI. So here we allow the MI to defer NI. So that means we allow the missing values in time varying covariates. And ZI is a collection of observed time varying covariates with measurement error. And this is our observed data, YI, ZI, TI, and CI. Now we proposed a semi-parametric nonlinear mixed effect response model with possible censored change points and mismeasured covariates. YG equal to GI, G1, TIG, beta IG star. So this part is for parametric part, as here GY is given, the beta IG star is individual specific and time-dependent parameters. And plus the second part is this is the response trajectories after the change point. So this is non-parametrically described. SITIG is a non-parametric part. This is the equal to G2, WT, and HIT. WT and HIT are unknown non-parametric smooth fixed effect and random effect functions. Here we introduced as TIG minus TS plus. This function is maximized TIG minus TI and 0. That means if that part greater than 0, that means we observe the change point, then we have the second part. Otherwise, we just have the first part. And plus random error term EIG. So here beta IG star is a function of ZIG star. Is dependent on ZIG star. It's true, but observed covariates ZIG star. And the beta star is population parameters. BI star is random effects. So here is a G1, D, G2 are known functions. So here we have some assumptions for this model. It's EI, it's a normal IID, it's BI, it's a IID normal. And the HIT is IID randomizations of zero mean stochastic precise. BI star and HIT are independent of EI. So now we consider dealing with the WT and the HIT. So we approximate them by linear combinations of some basis functions, psi p and phi q. So here we introduce new fixed effects and random effects coefficients, mu p and psi iq. So we consider the natural cubic splines with percentile-based knots as the basis functions, and use the AIC or BIC as a criterion for selecting the value of P and Q. Then substituting the WT and HIT by their approximations, we approximate our proposed semi-parametric nonlinear mixed effect model by the following parametric nonlinear mixed effect model. And here we have the standard assumptions for the nonlinear mixed effect model. In the presence of measurement errors and missing data in time-varying covariates, we need to model the covariate precise. Here we consider the multivariate linear mixed effect model for the covariate. ZIL, so here is equal to UIL alpha plus VIL AI plus epsilon IL. So here is the UIL and the VIL are Dirac matrices. Alpha and the AI are fixed and random effect parameter vectors. Epsilon IL is random measurement errors as time UIL. Here we assume the two covariate values ZIGL star equal to the first two terms. And we also have the normality for the AI, and AI and the epsilon I are independent. Both of them are independent of EI and BI in response model. Now we look at the time to change point. So the time tau I to change point is likely related to the longitudinal response and the covariate precises. So we assume tau I follows some distribution depending on the AI and the BI. For example, we can use log normal as log tau I as a linear regression on the AI and the BI. So plus error term. And here we introduce some parameters gamma and eta. So it's here we can assume it's the error term theta follows normal distribution with mean 0 and standard deviation eta. So based on these three models, response model, covariance model, and the times to change point model, so we propose the two-point likelihood methods for the MLE of parameters in the model. So first method called MCEM method implemented by the Monte Carlo EM algorithm. The second method called the APPR method, where we approximate log likelihood functions by using the first order Laplace approximation. So now we look at the log likelihood function. So we collect all model parameters denoted by theta, And we can write down the observed data log likelihood function of theta. So you can see this is a double integral with respect to AI and BI. So it's this function L O theta, as generally doesn't have the closed form expression. To get MLE, we treat the random effect as the missing value. So we have complete data, and we can write down complete data log likelihood function of theta. And then we have the MCEM algorithm. So this is the EM algorithm. So each step, we use Monte Carlo method to evaluate conditional expectation for the complete data log likelihood function LC theta given observed by data. And in M step, we will use standard maximization procedures to maximize this summation of a conditional expectation of LC theta to update the parameter estimates. We can iterate between each step and M step until the convergence. So we will get MLE of theta, denoted by theta height. And the last formula is for the various convergence matrix of MLE of theta height. So now we talk about why we need the second method, APPR method. So the MCEM method may be computationally intensive, and sometimes may offer potential computational problems such as slow or non-convergence, especially when the dimensions of random effect AI and BI are not small. On the other hand, the second method, the APPR method, avoids Monte Carlo approximation and just is always computationally feasible. And also the second method, the APPR method, can be used to obtain good parameter starting values for MCEM method. So for the APPR method, so first we defined a new function, P W height LC theta. So here, what is W? This is W is the collection of random effects AI and BI. And this new function depends on the LC theta and the second derivative of LC theta with respect to the WI. And WI height is a solution to the first derivative of complete data log likelihood function with respect to the WI equal to 0. This is that solution to these equations. It can be shown that W height LC theta is the first order Laplace approximation to observed data log likelihood L O theta. And then we propose an iterative algorithm for approximate MLE of theta based on this new function P. So this algorithm includes the step 1, step 2. Step 1, we update WT plus 1 by maximizing the LC theta T with respect to W. And the second step is we update theta T plus 1 by maximizing P W T plus 1 LC theta with respect to theta. So we iterate between step 1 and step 2 until convergence. So we will get approximate MLE of theta denoted by theta AP height. The last formula is for the various covariance matrix of theta approximate MLE theta P AP height. In theory, we have the consistency and asymptotic normality of theta AP height. Now we look at an example in AIDS studies. Here we have 45 HIV patients treated by some antiviral viral drugs. very low CD4 cell count and other variables were repeatedly measured over a period of 48 weeks. The number of individual measurements for each individual varies from 4 to 10. There were rebound points on 15 very low trajectories. Based on the biological arguments, so we have the very low model here. YIG is equal to the first part is the parametric part. This is for the clear pattern at the beginning of treatment. And after rebound, we have the non-parametric part for very low trajectories and plus error. And here we use the AIC and BIC criterion to select the numbers of P and Q. So it's finally we approximate SITIG by this function. For CD4 cell count precise, we use the empirical polynomial linear mixed effect model. So AIC and BIC criterion are used again to select the best model as the finally the quadratic polynomial linear mixed effect model wins. Now for times to change points, we use the log normal. So this model. And then it's we report the parameter estimates for the main model parameters beta from in the example in table 1. Here is we have our posted method MCEM APPR. We also gave the results based on the naive method for comparison. Naive method ignores measurement errors in CD4 and the change points. So you can see the proposed two proposed methods gave us the similar estimations for beta. However, the naive method gave us some bias, some different estimates, especially for beta 4. This is the coefficient of CD4. This describes the effects of CD4. This is a negative 0.75, but another two methods gave us the positive. It's 1.81, 2.08. It's quite different. This figure shows us it's observed and fitted very low trajectories for randomly selected 3 HIV patients without and with change points. The left panel is without change point, right panel is with change points. So it's the solid line for the naive method, dashed line and the dotted line for the proposed methods. So you can see two proposed methods gave the better fitting than the naive method. Now we look at the simulation studies. So here we want to evaluate the performance of two proposed methods and also want to compare them with the naive method. The model is similar to the model is similar to the those in examples. So it's here. This is the simulation study results in table 2. So here is we have estimates. We give the true value and estimates based on the 3 methods. And the proposed 2 methods gave us the satisfactory results, produced satisfactory estimates However, the naive method gives some quite biased estimates for some parameters. And in terms of bias and the mean square error, we find the two proposed methods performs much better than naive method. And now I summarize the simulation studied and draw conclusions for this talk. So in this research, we consider joint modeling for semi-parametric nonlinear mixed effect models, which change points and covariate measurement errors and missing data. We proposed two joint likelihood estimation methods for all model parameters. Simulation results show that both joint likelihood methods produce satisfactory results. MCEM is much accurate than the APPR, while APPR is more computationally efficient than MCEM. On the other hand, the naive method, which ignores change point and covariate measurement errors and missing data, may lead to biased estimates. This is the references. Thank you very much for your attention.